Hello and good morning, everybody. My name is David Anu, and let me welcome you on behalf of the other presenters as well. I will start with the first talk, but first a quick general introduction about this webinar. The main goal of the session is to showcase approaches that greatly simplify the work of data analysts when performing data analytics or when employing machine learning algorithms over big data. This webinar is co-organized by the research project Infore, Smart Data Lake, and Extreme Earth. And with that, I will start with the first presentation about Infore. My talk will be about graphical data analytics and workflows and cross-platform optimization. So it's about the project I'm talking about is called Infore, short for Interactive Extreme Scale Analytics and Forecasting. And what is the general overview and the goal of our project? So we want to design data processing workflows in a graphical way so that data analytics tasks can be used without or only minimal programming overhead. What we want to do with that is we want to achieve real-time interactive machine learning and data mining, and also distributed complex event forecasting. And we're not doing this only for our own, but we work closely with three very interesting use cases, which I will quickly present you because it's not the main agenda of this talk. But the first use case is about life science. And here we are working on studying the effects of drugs and drug synergies in cancer. And we're doing this in silico simulation. So we have huge supercomputers. The supercomputer center in Barcelona is one of our partners. And there we are simulating the individual growth and reaction of tumor cells, how they react on medications and different drugs. And these are really huge simulations and very important research. But the challenge is that it's a huge amount of data and CPU time that is required. And of those many simulations, only a few run are promising. And it's really hard to shift through all these kinds of data and see which one are the promising ones and perhaps stop the non-promising ones quite early to save a lot of simulation time to speed up the research and get interesting results faster. The other use case is about finance data. And here we want to predict price swings and analyze systematic risks and perhaps do also forecasting on investment opportunities. And as you can imagine, this is also a huge amount of data that comes in very fast. And we want not only analyze single stock data or single time curves, but we want to do it on a high dimensional level, viewing patterns and correlations between very different market shareholders and see how the market reacts in a really fast way. And the third use case is about maritime traffic monitoring. So we are working here with Marine Traffic, a big company that is providing a monitoring service for maritime traffic. And we want to monitor ship movement and especially detect illegal activities such as ship fishing in areas where it's not allowed, piracy, and things like that. And the challenge here is that we have data coming in from a lot of different sources, like local data from underwater monitoring systems, sonar, microphones, and so on, land-based survey and surface-based monitoring, and of course global satellite positioning data and space monitoring via satellite. And the challenge here is that we have a large amount of data because we have many ships to monitor. We have a lot of different data sources available, as mentioned, and the actual event that we want to detect is classified because it's not a single binary decision. There's not a flag, okay, this is a pirate activity or not, or this is a fishing activity. but we have to extract these patterns out of the ship movement, of the past behavior of the ship, and so on. So this is quite complex to detect those things. So this is background on the technical side, on the use case side, what we want to do. And now I will go a bit and show how we do this in a technical level, so what we have achieved so far in this project. So we at RapidMiner, we have built a graphical data analytics workflow that works with Spark Streaming and Flink. And what we have here is we have a graphical editor that is a typical work approach from RapidMiner, how we design also data analytics and machine learning processes, and we have adopted that for streaming analytics. So what you see here is really an actual screenshot of the RapidMiner workflow designer, and we see here as a new feature the streaming nest, inside which we will build the streaming analytics workflow. So we define a connection to which cluster we want to, what cluster we want to connect. Inside we define from where we want to retrieve the data, typically coming from a Kafka topic provider. There we retrieve the data from the different topics, and we can perform typical analytics tasks such as filtering, mapping keys to another value, and of course joining streams and perform some aggregations on that and then write back. So it's a very quite simple and quick method to design these analytics workflows, and upon execution, one job is created that is then executed on a specific cluster. How does it work on a technical level? So we see the representation inside RapidMiner Studio with the operators that you can quickly, easily drag and drop and connect. Behind, then it is translated, visual representation is translated into a framework independent graph that is a general description about this workflow. And from that independent graph, it is then specifically translated into the specific graph for the different clusters. So, for example, Spark or Flink. And yeah, what we have achieved so far, we are supporting Apache Flink and Apache structured streaming. We have already several operations available, like typical streaming analytics operations. We have a connection to quite powerful Synopsys data engine that is performing more advanced calculations on the streaming data, on the incoming data. We have connections to custom online machine learning engines that are running on Flink and Akka. And we already have some connection to financial service providers that we can also collect the data. What are the benefits of this approach in this workflow? So first of all, it is a code-free development. So you don't have to write specific code in a language like Java, Scala, or Spark to design your workflows. And as you have seen, because we are using RapidMiner as a front end, it's completely independent of the backend. So we can easily switch out the underlying cluster and the underlying backend. Another nice feature is we have a pluggable connection management. So all the connections information to which cluster we want to collect, from which Kafka data provider we want to collect the data, this is all manageable via this connection object, and they can be easily plugged out. So it's more or less one simple operation, for example, to switch from a staging environment to a productive environment and back and forth. So this is really easy. And because we have this independent representation, these processes can also easily share and with other colleagues and working on other systems, or even via RapidMiner server and AI Hub, you can collaborate together on designing these workflows. If you want to look a bit more, because time is quite short, we have, not showing it, I will post it in the chat later. Here we have a YouTube video where is presenting a bit more in details how it's really executed, what is working in behind. I'm not sure why the link is not showing here. I will post it in the chat after my presentation. So what we want to do is not only about having a single graphical workflow, but we want to also have customization. And as you see here, we now have another connection between Spark Streaming and Flink, and we have a new component, the optimizer. And what this optimizer is doing, we start if you have a multi-setup, we have several clusters available in a huge infrastructure. The optimal execution can depend on different aspects. For example, obviously, what resources are available, how many nodes each cluster has, how many memory is available, how many CPUs are available, how many different parallel tasks can be executed. And of course, where the data is located. Does not make sense if we have a very fast cluster, but the data has first shipped via internet to it. So you have a large lag on the data for the data transferring. It's probably not as feasible. And of course, there are always software performances and implementation details. Some operations might run faster on different backends, or specific operations might only be available on different backends. So overall, an optimized process layout and the optimal backend exchange between different clusters can greatly enhance the performance of such a workflow. And how we can do this? As you see here, we have a file layout as before, but a small different changes. So example, here we have now the streaming optimization. I have to rush a bit because time is running short already. And we define different backends. Now we have here Flink execution backend and a Spark execution backend. And this layout then is sent over to the optimizer. And the optimizer gives us a response. So it says, okay, put these execution tasks on the Flink platform and these operations on the Spark platform. And with that, the workflow is split at that point. And then we have two new executions. One nest for the Flink execution and one for the Spark execution. And inside, the same operations apply. So, okay, here we apply the filtering and the join of the streams from on Flink, but the mapping is done on Spark. And in the end, here again, we have this Kafka sink and this Kafka source. They are interconnected. So the data coming out of this cluster and this operation comes in here for the join on the Flink cluster. And with that, we come to an optimized workflow in the end. So the conclusion so far, what I have presented you is we have seen the three very interesting use cases we are working on: maritime data, finance data, and the life science use case with the cancer research. You have seen a first version of the graphical editor, how you can design and manage streaming analytics workflow with a very easy user interface. And you have seen how we can perform cross-platform optimization. So of course, the project started last year, so we're not yet done. We have a lot of things to do and a lot of very good ideas what we want to implement next. So what we are doing is, and currently working on, is a better job in data monitoring. So we want to see actually what is doing, what we are doing and what's happening on the streams. Also to scale up live the demands on the cluster. We want to have a better and tighter integration with the high-performance computing systems that are run for the simulations, especially for the cancer simulations. So we have an interconnectivity there, or a tighter interconnectivity there. And of course, we want to do some refinements and deployment of the actual use cases. So we want to see some good results here, but we are very convinced that this will work. And with that, my 15 minutes are already over. So thank you a lot. And now I will hand over to